NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve floor function equations using the definition. We will follow a precise 3-step algorithm and apply it to an example. We will now walk through a complete example, step by step. Solve the equation, floor of 2x minus 1 equals 4. We begin with the definition. If the floor of f of x equals n, then n is less than or equal to f of x, and f of x is less than n plus 1. Step 1. Identify the integer n. Here, the right side is 4, which is an integer, so n equals 4. Step 2. Apply the definition. Replace the floor with a double inequality using n equals 4. That gives 4 less than or equal to 2x minus 1, and 2x minus 1 is less than 5. Step 3. Solve the double inequality for x. First, add 1 to all 3 parts. Then, divide everything by 2 to isolate x. Let us visualize the solution on a number line. A closed point at 2.5 and an open point at 3, with the interval shaded in between. Therefore, the solution set is all x in the interval from 2.5, inclusive, up to 3, exclusive. Here is the example. The problem is, open bracket x, floor of x, close bracket equals 1. Step 1. Apply the floor function definition. We use floor of u equals k if, and only if k is less than or equal to u and u is less than k plus 1. Therefore, floor of x floor x equals 1 implies 1 is less than or equal to x times floor x, and x times floor x is less than 2. Step 2. Substitute integer and fractional parts. Let x equal n plus p, where n is the floor of x and p is the fractional part of x with 0 less than or equal to p less than 1. Substitute into the inequality to get 1 is less than or equal to n squared plus pn, which is less than 2. We label this as capital I. Step 3. Analyze n equals 1. Substitute n equals 1 into inequality capital I to get 1 is less than or equal to 1 plus p less than 2. Subtract 1 to get 0 less than or equal to p less than 1. Therefore, x belongs to the interval from 1 inclusive to 2 exclusive. Step 4. Analyze other integer values for n. For n greater than or equal to 2, n squared is at least 4. So n squared plus pn is at least 4, which cannot be less than 2. For n equals 0. The middle becomes 0, violating 1 less than or equal to 0. For n less than or equal to negative 2, the values exceed or equal to and cannot satisfy the strict upper bound. Thus, no solutions arise in these cases. Step 5. Analyze n equals negative 1. We have 1 less than or equal to 1 minus p, which is less than 2. This yields 0 less than or equal to negative p, which is less than 1, implying p equals 0, because p must also satisfy 0 less than or equal to p less than 1. Therefore, x equals negative 1. Step 6. Combine the solutions. We unite the interval from 1 inclusive to 2 exclusive with the point negative 1. That is the complete solution set. Example. We will solve the equation floor of sine x equals floor of cosine x. First, we display the problem clearly. Step 1. Analyze the possible floor values. Since sine and cosine both lie between negative 1 and 1, the floor can only be negative 1, 0, or 1. We also separate the exact value 1 as a special endpoint. Step 2. Case 1. Both floors equal negative 1, which means sine and cosine are between negative 1 and 0, excluding 0. On the unit circle, that is the third quadrant, angles from pi to 3 pi over 2, endpoints excluded. Step 3. Case 2. Both floors equal 0, which means sine and cosine are in the interval 0 to 1, including 0, but strictly less than 1. On the unit circle, that is the first quadrant, angles from 0 to pi over 2, endpoints excluded, because at those endpoints one of the functions is 0 or 1. Step 4. Case 3. Both floors equal 1 would require sine x equal 1 and cosine x equal 1. But sine x equals 1 at pi over 2 plus multiples of 2 pi, while cosine x equals 1 at 0 plus multiples of 2 pi. These never occur at the same x, so this case has no solution. Step 5. Combine the solutions from the first two cases. The complete solution set is the union of the first quadrant open interval and the third quadrant open interval, each shifted by integer multiples of 2 pi. Recap. We used the ranges of sine and cosine with the floor function, solved by quadrants, rejected the impossible case where both floors equal 1, and combined the valid intervals. We will solve the equation, floor of sine x plus cosine x equals -2. We'll proceed step by step using the floor function definition, a sine plus cosine identity, and a unit circle view to find all solutions. Step 1. The rule says, bracket u equals n if and only if n is less than or equal to u, and u is strictly less than n plus 1. Applying this to our problem, we get -2 less than or equal to sine x plus cosine x, and strictly less than -1. Step 2. Use the identity sine x plus cosine x equals square root of 2 times sine of x plus pi over 4. Also, the range of sine x plus cosine x is from negative square root of 2 to positive square root of 2. Therefore, the inequality is effectively negative square root of 2 less than or equal to sine x plus cosine x, and strictly less than -1. Let theta equal x plus pi over 4. Then the left side becomes square root of 2 times sine theta. Dividing by square root of 2 gives sine theta in the interval from -1 to -1 over square root of 2, not including the right endpoint. To visualize the theta interval, let's use the unit circle. The values where sine theta is less than -1 over square root of 2 lie strictly between 5 pi over 4 and 7 pi over 4. Hence, theta is in the open interval from 5 pi over 4 to 7 pi over 4, plus any multiple of 2 pi. Step 3. Substitute back using theta equals x plus pi over 4. Subtracting pi over 4 from the interval bounds gives x in the open interval from pi to 3 pi over 2, plus any multiple of 2 pi. To build further intuition, look at the graph of sine x plus cosine x. The purple line shows y equals -1. The shaded orange band marks the x values between pi and 3 pi over 2, where the function is below -1. Therefore, the complete solution can be written as the union of open intervals from pi to 3 pi over 2 shifted by multiples of 2 pi. Quick recap. We used the floor definition to form an inequality. Then we combined sine and cosine into a single sine function with a phase shift. We solved the resulting sine inequality using the unit circle and converted back to x. We show the example label. We split x into its integer and fractional parts. By definition, write x equals n plus p with n an integer and p between 0 and 1. Now substitute this into the equation. Next, we use the property of the floor function with integers. The floor of n plus y is n plus the floor of y. Also, the floor of p is 0, since p is between 0 and 1. Apply these to simplify the equation. Clear the fraction by multiplying both sides by 3. Then solve for n explicitly. Because p is between 0 and 1, p plus 3/8 ranges from 0.375 to 1.375. So the floor of p plus 3/8 is either 0 or 1. Case 1, floor equals 0, which means p is less than 5/8. Substitute into n equals 3 times floor minus 7p plus 2. Solve for p in terms of n, and apply. Floor equals 0, which means p is less than 5/8. Substitute into n equals 3 times floor minus 7p plus 2. Solve for p in terms of n, and apply the bounds. We list the valid integer and the p-values and compute x equals n plus p. Case 2, the floor equals 1, which means p is at least 5/8. Substitute into the expression for n and solve, keeping the bounds consistent. Then compute the corresponding x values. Finally, we union the solutions from both cases. Here is the complete solution set in increasing order. Let us summarize. We split x into integer and fractional parts, used floor properties, and handled 2 cases based on the fractional shift by 3/8. Quick challenge. Can you predict how the solution changes if 3/8 is replaced by 1/4? Fractional parts, used floor properties, and handled 2 cases based on the fractional shift by 3/8. Quick challenge. Can you predict how the solution changes if 3/8 is replaced by 1/4? If 3/8 is replaced by 1/4? Example. In this example, we will solve the equation square root of x plus bracket x plus square root of x minus bracket x equals 1. Throughout, the square brackets denote the floor of x. Step 1. Determine the domain. For any square root to be defined over the reals, the expression under the radical must be greater than or equal to 0. We apply this rule to both radicals. Step 2. Check for solutions within the domain. We analyze the sum of the two radicals for different ranges of x. First, if x is greater than or equal to 1, then x plus bracket x is at least 2. Its square root is at least square root of 2, which is greater than 1, and adding a non-negative term pushes the sum above 1. Therefore, no solutions with x greater than or equal to 1. Next, consider 0 less than or equal to x less than 1. In this case, the floor of x is 0. The equation reduces to 2 times the square root of x equals 1. Solving gives x equals 1/4. We verify that this satisfies the original equation. Therefore, the equation has a unique solution in the real numbers x equals 1/4. We will solve the equation nx minus open parenthesis north plus 1 close parenthesis floor of x equals 0, following the provided step-by-step algorithm. Step 1. Variable substitution. We decompose x as its integer part plus fractional part. Write x equals floor of x plus p, with p between 0 inclusive and 1 exclusive. Step 2. Substitution. Use substitution property. Replace x by open bracket x close bracket plus p. Step 3. Expand the terms. We apply the distributive property. Expand n times open bracket x plus p close bracket. Step 4. Simplify. Rewrite minus open parenthesis north plus 1 close parenthesis floor of x as minus n floor of x minus floor of x to separate terms and reveal cancellation. Step 5. Isolate the floor of x. Cancel n floor of x on both sides. You get np equals floor of x. Step 6. Determine the range of the floor. Scale the inequality by n. From 0 less than or equal to p less than 1, we get 0 less than or equal to np less than n. Since np equals floor of x, we have 0 less than or equal to floor of x less than n. Step 7. Define integer values. Let floor of x equal k, an integer from 0 up to n minus 1. Step 8. Solve for p. From np equals floor of x, substitute k to get p equals k over n. Step 9. General solution for x. Write x equals floor of x plus p, which becomes k plus k over n, that is k times open parenthesis north plus 1 close parenthesis over n. Summary. Recap the key ideas and the final family of roots. Final result. X equals k times n plus 1 over n, where k is 0, 1, up to n minus 1. Quick challenge. Pause and verify that each k in the set produces a valid x with fractional part p between 0 and 1. We will solve the equation floor of x over 4 equals floor of x over 4, following the exact 4-step algorithm from the prompt. First, we present the example and the orange problem statement. Step 1. Because the left side, floor of x over 4, is always an integer, the right side must also be an integer. We define that common integer to be k, where k is an integer. Step 2. We multiply both sides by 4 to solve for the floor of x. This gives floor of x equals 4k. Step 3. Using the definition of the floor function. If floor of x equals n, then n is less than or equal to x, and x is strictly less than n plus 1. With n equal to 4k, we get the interval 4k is less than or equal to x, and x is strictly less than 4k plus 1. Step 4. We verify by substitution and finalize the solution set. Divide the interval by 4. We get k is less than or equal to x over 4, and x over 4 is strictly less than k plus 1/4, so the floor of x over 4 is exactly k. This matches the right-hand side value k. Therefore, the equation holds for all such intervals. To summarize, we define k as an integer to match both sides, deduced floor of x equals 4k, used the floor definition to bound x in the interval 4k to 4k plus 1, and verified the original equation. Here is a concise summary and a suggested next topic. sides. Deduced floor of x equals 4k. Use the floor definition to bound x in the interval 4k to 4k plus 1 and verify the original equation. We will solve the floor equation step by step, exactly following a clear algorithm. First, we show the label example. Then we present the problem in bold orange math. Floor of 2x equals floor of x. Rule. Hermite's identity for the floor function says floor of 2x equals floor of x plus 1/2. Step 1. Apply Hermite's identity. Replace floor of 2x with floor of x plus 1/2, keeping the right side as floor of x. Rule. Subtraction property. If a plus b equals a, then b equals 0. Step 2. Simplify the equation by subtracting floor of x from both sides. We obtain floor of x plus 1/2 equals 0. Rule. Definition of the floor function. If floor of u equals 0, then u is between 0 included and 1 excluded. Step 3. Convert the equation to an inequality using that definition. Therefore, 0 is less than or equal to x plus 1/2, and x plus 1/2 is less than 1. Rule. Solving chained inequalities. If it is less than or equal to x plus c, and x plus c is less than b, then subtracting c gives a minus c is less than or equal to x, which is less than b minus c. Step 4. Isolate x by subtracting 1/2 from every part. We write 0 minus 1/2 less than or equal to x less than 1 minus 1/2. Finally, this simplifies to minus 1/2 less than or equal to x, and x less than 1/2. The solution set is all x between minus 1/2 inclusive and 1/2 exclusive. This is the final answer. Now, a quick summary. We used Hermite's identity for floors and x less than 1/2. The solution set is all x between minus 1/2 inclusive and 1/2 exclusive. We will solve a floor function equation by following a clear, structured set of steps. First, we show the example and the problem in bold orange math. Step 1. Apply the floor function shift by integer rule. The rule says, for any integer n, the floor of x plus n equals the floor of x plus n. We will use this to pull the integers plus 3 and minus 5 outside the floor brackets. Quick challenge. Can you spot the integers we will move outside? Now, apply the rule to transform both floor terms. Step 2. Use the distributive property of subtraction to remove parentheses carefully. Remember, minus open parenthesis, a minus b close parenthesis equals negative a plus b. Now we simplify and combine the terms. Step 3. Combine constants. The floor of x and negative floor of x cancel to 0. We are left with 3 plus 5 equals 8, which simplifies to 8 equals 8. Step 4. Determine the solution set. Because 8 equals 8 is an identity, it is always true. The equation holds for every real x. Therefore, the solution set is all real numbers. Let us summarize. We used the shift by integer rule for the floor function, canceled the variable terms, observed the constant identity, and concluded that every real number satisfies the equation. Next, practice problems where the floor terms do not cancel. Example, we will solve the floor equation. Floor of x plus 4 minus floor of x plus 1 equals 2 using a precise, rule-based, step-by-step approach. Step 1. Apply the integer shift property of the floor function. It says, for every integer n, floor of x plus n equals floor of x plus n. We can pull 4 out of the first bracket and 1 out of the second bracket. Quick challenge. Why are we allowed to move those numbers outside the brackets? Because they are integers. Step 2. Simplify the expression by distributing the negative sign into the second parenthesis and then remove the parentheses. Notice that floor of x cancels with minus floor of x. Step 3. Combine like constants. For minus 1 is 3, so we obtain 3 equals 2, which is a contradiction. Step 4. Conclude the solution. A false statement like 3 equals 2 means there is no real number x that satisfies the equation. The solution set is empty. Summary. We used the rule floor of x plus n equals floor of x plus n to simplify the equation. After cancellation, we reached 3 equals 2, a contradiction. Therefore, the solution set is empty. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.